The next topic is the photons momentum and the Compton scattering. But then first of all, before about the photon momentum, right? So let me just give you the basics idea of physics related to the photon momentum first. It's called the relativistic momentum and the energy, okay, by Einstein in 1905 here. So when we have the particle of the mass m0 moving with the speed v, but now the speed v is about the 0.3 the speed of the light in the vacuum, or to the speed of the light here, okay. So it means that the speed of the particle is very large compared to the speed that we get used to nowadays, right? So let's define the Lorentz factor first, okay. We use symbol as the gamma is equal to the 1 over the square root of the 1 minus v square over the c square. So if we draw the plot between the gamma as the vertical axis and the v over c as the horizontal axis, right? So the graph will look like this one. So now you can see that when the v, which is getting close to the c, so it means that the v over c just getting close to 1 here, okay. So the gamma will blow out to the infinity. So that's making sense, because if you plug in the v over c equal to 1 into this equation, right, you will get 1 over the 0, which is close to the infinity, okay. Then but then if the v over c is less than the 0.3, the gamma is just about equal to the 1, okay. But if v over c greater than 0.3, so the gamma just tends to the infinity here. So in this case, it means that we can separate the mechanics into the two parts. The first one is the classical mechanics. So we can use the Newtonian mechanics to solve the problem, okay, if the speed of the particle or the speed of the object is about or less than the 0.3 times speed of the light in the vacuum here. But now if the speed of the particle, the speed of the object is greater than this value 0.3 times the c, right? So we just call it as the relativistic mechanics here. So then you need to use this type of the equations to solve for the problem. Then we can define the relativistic momentum as the p equal to the m0 times the v. So you can see that so far, right, we have known that p equal to the m times the v, okay. So that's why when we're talking about the speed is very low compared to the speed of light in vacuum, okay. But now if we talk about the speed is very large, then we need to multiply the gamma at the front here, okay. So then we can get the p equal to the gamma times the m0 and then times the v. And then we talk about the rest energy. What is the rest energy? The rest energy is to be the energy of the particle which just stay at rest, okay. Actually it just the conversion between the mass of the particle and then the energy of of the particles, okay. So we have the E0 equal to the M0 and then times the c square, the famous equation that you have seen many times already, okay. So this equation will say that the mass and energy are just the same thing, okay. It's just the same as when you have solid, liquid and the gas. So the solid can convert to liquid, liquid can convert to the gas, and the gas can go back to the liquid and go back to the solid, right? So we know that solid, liquid and the gas of the substance are just the same thing, but they just have the different phase or different states, right? So now the same for this question, the mass and energy are just the same thing. So we can convert the mass of the particle to be the energy as well. And also we can just convert the energy to be the mass, okay. So we can just create, or we can just build the particle by the energy. So this will be the meaning of this equation, okay. And then we talk about the relativistic kinetic energy, right? So we have the K equal to the gamma minus 1 and then times the m naught c square. Okay, so don't forget that this equation is the general equation. When we when we have the non-relativistic movement or the motion, right? So then we can convert this equation to be the K equal to the 1/2 the m naught and the v square. Okay, so we can just convert this equation for the general in the general case to be this one for the non-relativistic movement. Okay, but I mean, I will ignore. I will not show how we can just transform this to be this one. And then the next thing is the relativistic total energy. So it's going to be equal to the less energy and then plus the kinetic energy of the particle. Okay, so it means that when you combine this equation and this equation together, so you can see that m naught c square and minus 1 m naught c square here just cancel out. So we have only the gamma and then times the m naught c square here. And then finally, we have the energy momentum relation. Okay, so it is the E square, okay, the relativistic total energy square equal to the momentum of the particle and then times the speed of the light, okay, and then square, and then plus the less energy square. Okay, this is called the energy momentum relation. And then to derive the momentum of a photon, okay, we are going to use this relationship. Okay, we're going to use this relationship to find the momentum of the photon. Okay, so we know that the photon, right, can transfer a quantized energy, okay, which is equal to the h times the f. Then if the photon behaves as a particle, it should transfer the momentum as well, okay, the same as the conventional particle. Okay, so then Einstein proposed that the momentum of the photon, okay, the momentum of the photon is, okay, let's use this one. Because a photon, right, doesn't have the mass, it means that the m naught is just equal to the 0. Okay, m naught equal to the 0. So then we have that the E equal to the P times the C. Then we can get that the momentum is P, right, equal to the E and then over C. But we know that E equal to the h and then times the f and then over c. Then we can get that the f over the c, right, equal to what? It just equal to 1 over the wavelength. Okay, just equal to the 1 over the wavelength. So then finally we can say that the momentum of the photon, right, equal to the energy of the photons over the speed of the light in vacuum, and then equal to the Planck constant and then over the wavelength here. Actually, you have seen these equations already in, let's say, in this one, right, the EM wave. Okay, so I talk about this one in this topics. Where I said, yeah, this one. Okay, P equal to the E over C. Okay, we have seen this one already from this chapter. Okay, so let's look at this example. A laser pointer gives the 600 nanometer light beam of the power the 5 milliwatts. Okay, so now for the part A, calculate the momentum of each photon. Okay, so that's easy because we just want to find the p, okay, and we know the Planck constant and we know the wavelength. So then let's use p equal to the h and then over the lambda equal to the Planck constant, right? Just the 6.626 times 10 to the negative 34, okay, joules times second. And now for the momentum, for the wavelength, right, the 650 nanometer, we have the 650 times 10 to the negative 9 meter, right? Then finally we can get that the momentum is 1.02 times 10 to the negative 27 kilogram times meter over the second, okay, which is, you can see, really, really small, right? Which is really, really small. Okay, so now for the part B. How many photons are in 1 second? Okay, how many photons are in 1 second? So then again, so actually this one just similar to the previous examples. Yeah, kind of this one, that's the same. So we say that, oops, where is it? Okay, number of the photons, right? Number of the photons per second equal to, okay, so let's copy this one. Number of the photons per second equal to, okay, so this will be the power of the light, okay, and then over the energy of each photon, right? Equal to the power of the light beam, and then over energy of each photon. Equal to, okay, so the power of the light beam, right, equal to the 5 milliwatt here. Let's just write down, equal to the 5.00 times 10 to the negative 3, okay, so this is going to be what, which is the joules per second, and then over the energy of the each proton, okay, so then we can use this relationship, the energy in the EV, right, equal to the 1240 electron volt nanometers, and then over the wavelength in the nanometer here, okay, so it just 1240 electron volts and then times the nanometer, okay, and then over the wavelength, which is equal to the 650 nanometer. So now you can see that unit of the nanometer just cancel out, right? But here we have unit of the EV and the joules, okay, so we need to take we need to get rid of these two as well. Then I'm going to convert the EV into the joules. So we say that 1 EV, okay, 1 EV equal to the 1.602 times 10 to the negative 19 joules, okay. So you just clearly seen that unit of the EV just cancel out, and then unit of joules cancel out as well, and then also for the nanometer, right? So here we have 1 over second left, which is number of the photons per second. Then finally it's gonna be equal to 1.63 times 10 to the 16, okay, photons per second, and this is answers. Okay, so now you have learned about the momentum of the photon already, okay, And then we need the experiment. Okay, we need the experiment to show that the photon really have the momentum. Okay, so one experiment is the Compton scattering experiment. This one, okay, the Compton scattering experiment in 1923 by Compton. Okay, so the idea is let's say that, okay, let's just look at this model. We have electron, okay, we have electron with the mass of the electron, right, equal to the me. Okay, the mass equal to the me. And then if we illuminate the electron with the X-ray with the wavelength equal to lambda naught here. Okay, so we just charge this electron with an X-ray with the wavelength equal to the lambda naught. So now, if we use the classical model, okay, if we use the classical model, we should expect that the scattering X-ray, right, should have the same wavelength as the lambda naught. So this idea is just the same as when you have interface, okay. Let me just write. You have the interface maybe between the air and the glass. So if you charge the visible light, okay, with the wavelength maybe equal to lambda naught, and we know that, okay, some of them must be scattered into this direction, okay. And then if we measure the wavelength of this reflecting wave, right, we should get the wavelength again equal to the lambda naught. So these two must be the same, right? But now here is the different things. If we charge the wavelength lambda naught, but then we get the scatter X-ray, right, to be the lambda palm. Okay, so this is beyond the expectation. And also we have the velocity of the recording electron, right, to be the v, okay, making the angle phi to this horizontal axis here. Okay, and then the experimental results said that the wavelength of the scatter X-ray lambda palm, or this one, increases compared to the lambda naught. It means that the lambda palm is greater than the lambda naught, okay, from the experimental results, and depends on the scatter angle, okay, depending on the theta here. So in this case, it means that if we have a detector at this position, right, so now we can just move detector, okay, on on this circular arc, okay, and now this detector will just make the angle theta to the point of the collisions at this position here, okay. Then we can measure the intensity of the X-ray as the function of the wavelength, okay. Then we can have the graph look like this one. So let's look at when the theta equal to 0. So it means that this detector is at this position, okay. So you can see that we have only one peak, okay, we have only one peak here. So it means that when we have the incident X-ray, right, coming to this and then scatter with the electron, right, so now the scatter X-ray that coming into this direction will have the same wavelength as lambda naught, okay, the same as this one. But now if we move this detector away from this central line or central axis, okay, for example at the 45 degree, 90 degree and 135 degree, so you can see that the lambda palm, right, will be increased more and more and more, okay. Lambda palm is increased more and more and more. It means that the wavelength of the scatter X-ray, right, will be increased, okay, because and it just depends on the scatter angle theta as well. So that's the experimental results that we can get. So now then, Compton used the idea of Einstein that the photon have the momentum, okay, and then he considered this as the he considered this one as the elastic correlation. Okay, he just considered this one as the elastic correlation. So then we need to use the conservation of the momentum and conservation of the energy to solve for this one. Okay, so we will work about this one later. Then he will have this equation. Okay, so delta lambda here equal to lambda palm, so it's mean the wavelength of the scatter X-ray, right? And then minus the lambda naught, which is the wavelength of the incident X-ray. So this is called the Compton shift. Okay, just called the Compton shift. It's going to be equal to this constant. Okay, this constant is just called the Compton wavelength, equal to this value. Okay, equal to the 2.426 picometer. And then times the 1 minus the cosine theta. Okay, 1 minus cosine theta. Okay, so then let's consider the theta first. Then from this picture, right, from this picture, okay, you can see that the theta can be ranged from what? From the 0 degree and then to the 180 degree, right? 0 degree just means that the scatter X-ray just come to this direction, okay? And then to the 180 degree just means that the scatter X-ray just in the back scattering, something like this. Okay, then it means that, okay, it means that the cosine theta, okay, the cosine theta should be in the range of, okay, minus 1, right, to 1. Okay, from minus 1 to 1, because the cosine 0 equal to 1 and cosine 180 degree equal to minus 1 here. Okay, it means that if we plug in this into this equation, okay, so you can see that if the cosine theta equal to the 1, then delta lambda equal to the 0, or the lambda palm equal to the lambda naught. Okay, so we said that if okay, in this case, if the cosine okay, cosine 0 degree equal to 1, then we have that delta lambda equal to the 0, or the lambda palm equal to the lambda naught. So it's going to be this case. Okay, but then on the other hand, if the cosine 180 degree equal to minus 1, then we can get that delta lambda, right, is going to be equal to, okay, if this one equal to the minus 1, so 1 minus minus 1 equal to the 2. Okay, so we have the 2h and then over the me times the c. So this one is to be the largest Compton shift. Okay, or we can get that the lambda palm equal to the lambda naught and then plus the 2h and then over me times the c. Okay, now we said that the h over me times the c, or the Compton wavelength, right, is just about the picometer. So then this will be the reason why this gonna work, I mean, for the X-ray, but not for the visible light. Okay, because the visible light, the wavelength just range from the 350 nanometer, right, and then to the 350 nanometer, something like this. Okay, so if we add this quantum shift, for example, if we add the maximum shift, right, this one, so then it's going to be equal to the what, the 2.426 picometer, which is equal to 0.002426 nanometer. So you see, this value is quite small, right, compared to the wavelength of the visible light. So that's why we say that it's quite difficult to see the Compton shift in, I mean, for the visible light here. Okay, so let's look at this example before we derive this equation. Okay, so let's look at the example. No, actually we should work on we should work on this one first. So I need to add a page. Okay. So now let's derive the Compton shift equation. Okay, so let's derive the Compton shift equation. Okay, so then again let's assume that this correlation is the elastic correlation. Okay, let's assume that it's going to be the elastic correlation. Then we need to have the two conservation of a energy and conservation of the momentum. Okay, so let's talk about the conservation of the energy first. Okay, so let's talk about the conservation of the energy first. Okay, so now before collision we have what? Before collisions we have the energy of the incident X-ray, right? And we have the energy due to this less mass. Okay, we have the energy due to this less mass. So then we get that, okay, let's just start from energy of the X-ray. It's just equal to the hc and then over the lambda naught. Okay, so don't forget that incident X-ray we have the wavelength equal to lambda naught here, and then plus the less mass of the electron, right? It's just me times the c square. Okay, equal to, so now after collisions, right? Okay, it's going to be the energy of the scattered X-ray with the wavelength equal to the lambda palm, and then the total energy of this electron. Okay, so let's talk about the energy of this one first. We have the hc and then over the lambda palm. So don't forget that the scattered X-ray, right? We have the wavelength equal to the lambda palm, and then plus. Okay, so now it's going to be the total energy of this electron. Okay, but now electron has the motion, right? So it means that we need to combine the relativistic kinetic energy and then plus the less energy of the electron. Actually we have this one already. Okay, it is this equation. So this one equal to the less energy and then plus the relativistic kinetic energy of the electron equal to the gamma m naught times the c square, right? So then plus the gamma the me times the c square. Okay, so then finally we get that the hc over the lambda naught equal to the hc and then over the lambda palm plus the gamma minus 1. Okay, if we move this to the right hand side, and then times the mec square. Okay, this is going to be the first equation that we can get. Okay, so now the next thing is conservation of the momentum. Okay, so don't forget that the momentum is the vector, so we must have the conservation both along the x and along the y axis here. Okay, so let's consider the conservation of the momentum along the x-axis. Okay, so now for the axis, right, we have only, okay, for the initial momentum before collisions, we have only the momentum of the X-ray. Okay, so now we know that the equation is P equal to the h over the lambda. So we have h over the lambda naught, right? Equal to, okay. So now after collisions, then we have this momentum of the scatter X-ray, right? But don't forget that this momentum is just making the angle theta to the horizontal axis. So we need to break this vector into the two components, the horizontal one and the vertical one. Okay. So now for this horizontal one, it's going to be the cosine theta. So then we get that equal to the h, and then over the lambda palm times the cosine theta. So this is the momentum of the scatter X-ray, and then we need to combine the momentum of the recalling electron as well. Okay, so we need to use this equation for the relativistic momentum, the gamma times the m naught and then times the v. Okay, then we have, okay, we need to break this momentum into the angle phi, right? So it's going to be equal to plus the gamma times the me and then times the v, right? And then times the cosine phi, and that's it. Okay, now the last one is going to be the conservation of the momentum along the y-axis. Okay, the conservation of the momentum along the y-axis. Again, before collisions, okay, we don't have the momentum along the y-axis. It means that before collision here, the momentum along the y-axis equal to 0. Okay, so we have 0 here, equal to. So now for the y-axis, I mean after the collision, right, we have, okay, if we break these components into the vertical one, it's going to be the positive, but if we break this into the vertical one, it's going to be the negative, right? So now we get that equal to the h over the lambda palm and then times the sine theta. Okay, so don't forget that if we break this one out of the angle, okay, so it's going to be the sine, and then minus the gamma times the me v and then times the psi phi. Okay, times the psi phi here. Okay, that's it. So now we have 1, 2 and the 3 equations. Okay, we have the 3 equations. So then we need to get rid of, okay, we need to get rid of what? We need to get rid of v, right, and the phi. Okay, because in this equation we have only the lambda palm and the theta. Okay, so that we know the lambda naught. Okay, so we have lambda palm as a function of the theta here. Then, but now, I mean, for these 3 equations, we have the lambda palm, we have the theta, and we have v, right, and we have the phi here. It means that we need to get rid of v and the phi, right? And so for, okay, and so for lambda palm as a function of the theta. Okay, so I will not show this one. Okay, so I mean just work and at your home by yourself. Okay, so the thing is, when we just solve for the lambda palm as function of the theta, right, then you will get the Compton shift equation. Okay, you will get the Compton shift equation, which is this one. Okay, so just work by yourself at home. Okay, now let's look at examples. This one. Okay, so let's consider this example. An X-ray of the wavelength, the 10 picometer, is scattered the 110 degree, right, from its original path by the last electron. So in this case, it means that, so when we shine the X-ray into the electron, right, so it's gonna scatter maybe to this angle, okay, because this is 90 degree and this is the 10 degree. Oh no, 20 degree, sorry. So this combined to be the 110 degree, okay. So now for the part A, calculate the kinetic energy of the recoiling electron. So we just want to find the kinetic energy, right? So we need to look at the conservation of the energy here. Okay. Okay, so let's look at this one. We have, oops, sorry, let me move this. Okay, we have the hc over the lambda naught, and then plus the less energy of the electron, right? So me c square equal to, okay, equal to this one, hc and then over the lambda palm and plus, okay. So now don't forget that this term is the total energy of the electron. It means that it's going to be the combination of the less energy of the electron and then plus the relativistic kinetic energy of the electron, right? So we can just separate this into the two terms. The first one is going to be the less energy and then plus the kinetic energy of the electron, right? Because the question needs us to compute the kinetic energy, okay? So then we can get that the kinetic energy of the electron is equal to, so this just cancel out, okay, equal to the hc and then 1 over the lambda naught minus 1 over the lambda palm. So now we know this value, okay. What is this value? This value is lambda naught, okay. This value is lambda naught, you know this one, but we don't know the lambda palm. But then we can find the lambda palm using the Compton shift, right? Because we know the scatter angle here, okay. So now next step is let's find the lambda palm. Okay, from the equation, from this equation, okay, we said that the lambda palm is equal to lambda naught and then plus the Compton wavelength. The Compton wavelength is just the 2.426 picometer, okay, the 2.426 picometer and then times the 1 minus the cosine theta, okay. So now let's just plug in the number into this equation, equal to lambda naught is what? Is 10.0 picometer, right? And then plus the 2.426 picometer. So let me just neglect this unit, okay? And then times the 1 minus the cosine theta is 110 degree, right? Then finally you will get that the lambda palm is just equal to 13.3 picometer, okay. That's me the lambda palm here. And then we can have that the kinetic energy of the electron, right, is going to be equal to, okay. So now you need to be careful about the unit, right? We have the hc over the lambda. So this is looks familiar for you. Remember we have this relationship. We have the, what's that? We have the hc over the lambda, right, equal to the 1240 electron volt nanometer and then over the wavelength in the nanometer, okay. Don't forget that 1240 for the nanometer unit. But now here we have the wavelength in the picometer, right? Picometer. So it means that we need to convert from picometer to be the nanometer first. So now it's equal to the 13.3 times 10 to the negative 3 nanometer, okay? Because nano is 10 to the negative 9 and combined with 10 to the negative 3, right, to be the 10 to the negative 12, which is equal to the pico here. So then we have, okay, 1240, sorry. Okay, in the unit of the electron volts times nanometer, right? And then 1 over what's wrong? 1 over lambda naught, right? Just the 10.0 picometer, or just equal to the 10.0 times 10 to the negative 3 nanometer here. And then minus 1 over the lambda palm. Lambda palm is this value, the 13.3 times 10 to the negative 3 nanometer, and that's it. Okay, so now you can see that this unit, right, nanometer, just cancel out with this and this. Okay, so now we can just use the calculator to solve for this one. Then finally you can get that the relativistic kinetic energy of the electron, right, is just equal to the 13.8 kilo electron volt, okay, or just 10 to the 3 times electron volt here. Now for the part B, okay, now for the part B, we just want to find the ratio of the electrons kinetic energy, which is this one, and the initial X-ray energy, okay, initial X-ray energy, which is, okay, let's just start from here. Initial X-ray energy, right? Let's say that the E equal to the HC and then over the lambda naught, okay, because we know the lambda naught equal to 10 picometer, right? Equal to 1240 electron volt nanometer, and then over the lambda naught again. Lambda naught, right, it's just in the picometer, so we need to convert to the nanometer here. We have the 10.0 times 10 to the negative 3 nanometer. So this unit just cancel out, okay? So here we have that. Okay, if we divide these two together, it's just the 124, okay? It's just the 124. And let me combine this with the electron volt to be the kilo electron volt, right? So we have the 124 kilo electron volt. Then finally we can get that the Ke and then over the E, right, it's just equal to the 30.8 kilo electron volts, and then over the 124 kilo electron volt. So this unit just cancel out to each other. So then the answer is just equal to 24.8%, and that's it. So it means that, okay, the kinetic energy of electron, right, is going to take about the 24.8% from the initial energy of the photon or the X-ray, okay, and then the remaining energy is going to go for the energy of the scatter X-ray here, okay.